What's up guys, this is Massey. Welcome to another video. In this video I want to show you how to find out the percentage of electric power lost. Part A, when we have low electric potential difference and high current. If 1 times 10 to the power of 5 watts of electric power is transmitted through a long cable with a resistance of 1 ohm, find the percentage of electric power loss for an electric potential difference of 1 kilovolt. So voltage is 1 kilovolt, which is going to be 1000 volts, and power is given, which is 1 times 10 to the power of 5 watts. R is given, which is 1 ohm. We need to find out I. I is going to be P divided by V, because we know P equals to V times I, so I will be equal to P divided by V. So that's going to be 1 times 10 to the power of 5 divided by 1 times 10 to the power of 3. It's going to make it 1 times 10 to the power of 2 amp, or 100 amp. And that's the large current. Now the power lost in the cable to heat would be P equals to I squared R. So I will be 100 to the power of 2 times resistance, which is 1. So it's going to be 100 times 100 is going to be 10,000. 10,000 watts, or 1 times 10 to the power of 4 watts. So if you compare it with the original electric power, which was 1 times 10 to the power of 5, it means that that's 10% of it. So we have 10% loss of the original power. Part B, it says high electric power potential difference and low current. In this situation, if 1 times 10 to the power of 5 watts of electric power is transmitted through a long cable with a resistance of 1 ohm, find the percentage of electric power lost for an electric potential difference of 1 times 10 to the power of 5 volts. So in this part, part B, I'm going to say P 1 times 10 to the power of 5. We have voltage, so I equals to P divided by V, like the previous part. Voltage is 1 times 10 to the power of 5 as well, so ampere is going to be, the electric current is going to be 1 ampere, which is going to be much smaller. So power loss is going to be I squared R. So it's going to be 1 squared times R. R is 1, so it's going to be 1 watt. So as you see here, 1 comparing to 1 times 10 to the power of 5, it is very small. So it is going to be 1 divided by 10 to the power of 5, which will be 0.001% loss of the original power. So that means having a high potential difference and a low current is going to be much more efficient. So it is to increase high potential difference and to have low current, that's going to make it more efficient, and we're going to have less power loss. Now in this example, it says an electric potential difference of 5 times 10 to the power of 2 kilovolt is used to distribute 2 times 10 to the power of 2 kilowatt of electric power through a long cable with a resistance of 0.8 ohm. Find the percentage of electric power lost in the lines. So V is 5 times 10 to the power of 2 kilowatts, which is going to be 5 times 10 to the power of 5 volts, sorry, not watt, volt, Power is 2 times 10 to the power of 2 times 10 to the power of 3 watt, because it's kilowatts, we need to convert it to watt. So it's going to be 2 times 10 to the power of 5 watt. The resistance is 0.8 ohm. So in order to find the percentage of electric power loss, we need to find I first. I is P divided by V. P is 2 times 10 to the power of 5 divided by 5 times 10 to the power of 5. 2 divided by 5 is going to be 0.4 amp. So P will be I squared R. That's going to be the lost power. 0.4 to the power of 2 times 0.8. 0.4 to the power of 2 times 0.8 is going to be 0.128 volts. So that's going to be the power lost. So 0.128 divided by 2 times 10 to the power of 5 will be 6.4 times 10 to the power of negative 5% of the original power lost. Now, in this example, it says for each of the 2 transmission lines described below, determine the current and the power loss in the line. So let's start with the part A. We have power, 2 times 10 to the power of 2 kilowatts. We need to convert it to watts, so we need to multiply it by 1,000. It's going to be 2 times 10 to the power of 5 then, watts. R is 0.5 ohm. And potential difference is 1 kV, which is 1,000 volts. So I will be P divided by V, which will be 2 times 10 to the power of 5 divided by 1,000. That's going to be 200 amp. That's going to be a high electric current. So we need to expect high energy loss. P equals to I squared R. I is 200. The power of 2 times R. 0.5. That's going to be 200 times 200 times 0.5. It's going to be 20,000 watts or 20 kilowatts. So the percentage of electricity lost is going to be 2 times 10 to the power of 4 divided by 2 times 10 to the power of 5, which will be 10%, 0.1 or 10%, because of these high electric currents. Now in part B, power is 2 times 10 to the power of 2 kilowatt, which is the same thing. 2 times 10 to the power of 5 becomes. Resistance is 0.5 ohm. Potential difference is 100 kilovolts, or it says 1 times 10 to the power of 5 volt. We need to find current first. Current is going to be P divided by V. 2 times 10 to the power of 5 divided by 1 times 10 to the power of 5. 2 divided by 1 is going to be 2 amp. Then energy loss is going to be I squared R. 2 to the power of 2 times R, which is 0.5. 4 times 0.5 is going to be 2 watts. So that's going to be the power loss. Just compared with the previous part, in previous one we had 20,000 watts. This one we have only 2 watts lost. Why? Because of the difference in electric current. So the percentage of lost power is going to be 2 divided by 2 times 10 to the power of 5. It's going to be 0.001%. That's going to be the percentage of power lost. Next example. A generating station produces 15,000 kilowatt of electric power. Assuming 100% efficiency of transmission, calculate the current flowing through a 5 times 10 to the power 5 volt transmission line leading from a generation station. So P is 15,000 kilowatt, which will be 1.5 times 10 to the power of 7 watts. 100% efficiency, voltage is 5 times 10 to the power of 5 volts. So we need to find out the current. Current is going to be P divided by V. We have 1.5 times 10 to the power of 7 divided by 5 times 10 to the power of 5. So that's going to be 30 ampere. So that's going to be the electric current in the transmission line.